Welcome to UVU CS3060 Lecture 6.4, where we talk about how to solve the critical section problem using hardware. Let's begin. So we've seen that a software solution, while possible, is definitely not the best solution. Peterson's solution as a software solution generally works okay with a two-process or two-threaded solution, but still can run into hardware issues such as caching and caching synchronization. In the case where these particular software issues don't work, hardware vendors have realized that it's probably best to provide hardware support for implementing the critical section code. Now, the solutions we're going to talk about come from the talk of entering and exiting the critical section to locking and unlocking the critical section. So we're going to protect these critical regions with locks, and we'll use the term lock from here on out. Now, one way we could do this is we could lock this particular critical section by disabling interrupts. Really, this all occurs simply because we have a process that's being interrupted and then a second process coming in and overriding the values of the first. So we could disable interrupts, but it doesn't work very well on multiprocessor systems, just very, very inefficient. And it's just not a scalable solution. Any operating systems that try to use this run very slowly. So disabling interrupts, while it may work, is not an option. What really happens these days is modern machines provide special hardware instructions, atomic or non-interruptible hardware instructions, meaning that multiple things happen in this instruction, but nothing can interrupt the instruction until it's run to completion. So one of the ways is to test a memory and then set a value. Another way is to swap contents of two memory words as necessary. And this is a demonstration here of what we're going to be looking for with our critical section solution. We need to acquire a lock somehow, and we'll discuss that with hardware here shortly. Run the critical section and then release the lock so that other processes may obtain that lock. The first instruction we're going to talk about is called test and set. The test and set instruction actually accomplishes a couple of different things. First, it's taking a value, a Boolean, a character, or an integer value, taking that value, and it is remembering what the value was when it first entered. So our v is actually going to be the value of our target before we change it in the second step. So this instruction will always set target to true, but it will try to retrieve the value of target before setting it to true. That way, if the target has been set to another value, such as false, that false value can be returned, which could be very useful. Say, for example, we want to break out of a loop. We want it to continue to loop so long as the value was originally true, but the moment it's set to false, we want that false value to be retrieved, but we want the variable to be set back to true in one smooth atomic operation. We can see this in this particular code. We have a variable called lock. Lock, a reference is reference to lock is sent to this test and set instruction. Now remember, if lock is true, test and set is going to return true, and lock will still remain true. But if lock is set to false, test and set is going to return false, but lock will be set to true when it's done. Lock will always be set to true after this particular instruction, but it may return true or false depending on what the value of lock is. This is our spin loop or infinite loop, idle loop that continues checking. Once the test and set returns false, the critical section can be entered. And then we set lock to false. Remember, when we perform test and set retrieved a false value, but lock is set to true. When we finish the critical section, our exit sets lock to false, which allows any call to test and set to return false and break out of this loop. So this is how we can use test and set. I do want to point out here that consider if we have 3 threads. Let's say thread 1 performs test and set and gets false and is able to enter its critical section. Thread 2 and thread 3 come in here and start looping on this because lock is set to true. Thread 1 finishes and sets lock to false, which allows one of the threads to proceed forward. Let's give that to thread 2. Now, while thread 2 is in the critical section, thread 1 continues back up here and enters this test and set loop again until thread 2 decides to finish its critical section, at which point it sets lock to false. Now, there's nothing to say which thread 1 or thread 3, performs this unlock or gets the false value out of test and set. If it's thread 1, then we see an instance here where thread 3 is being denied forward progress. This actually breaks the bounded waiting condition of a good critical section lock. So just using test and set in this method is not a complete solution, especially in a multi-threaded environment. 2 threads, sure, and we'll see it work for us. But 3 threads, not so much. 4 threads really can start failing. So let's go ahead and look at another instruction. This instruction is called compare and swap. Now, what compare and swap does is it takes a value, a pointer to a value, goes ahead and saves that value in a temporary variable. Now, if whatever was in value matches expected, then value is set to new value. And then the original value of the value variable is sent back to the caller. Now, we can make this look like test and set just simply by doing value, having expected of 0, and a new value of 1. So if value is 0, it'll get set to 1. But if value is 1, then no change is made to this. This is actually a more efficient instruction in that it doesn't perform a write operation, and write operations to memory tend to slow things down. A read-only operation, those tend to be very, very fast and can rely on cache values. But compare and swap is similar to test and set. In fact, we can see in this particular piece of code where it's used just like test and set. Compare and swap takes the lock variable. If it's 0, it's going to get set to 1. Just the same way test and set would set the value to true, whatever the value was in there before. And then it will return whatever's in lock. Here's our critical section, and when we're done, lock is set to 0, which will allow this to break out for another process. Now, as I said, test and set by itself is not a particularly good way to protect your critical section, simply because it doesn't pass the bounded waiting condition. But here we have a bounded waiting solution using test and set. There are 2 variables that are used in this particular case. Well, 3 if you count the lock, of course. We have a waiting, which is an array. Each particular thread has an entry in this array. And we have a key. Now, the waiting, every time a thread wants to continue waiting for a particular lock, it will set its waiting array entry to true. It will then set key to true and constantly test to see if waiting and key is set. Now, key is loaded to the value of test and set, depending on what the lock variable is. So let's say test and set comes back false. If lock is unlocked, then key will be false and this loop will break. If waiting is set to false, then this will break. Now, if we come down here and take a look, whenever waiting is set to false, so whenever this loop is broken, either because waiting is false or key is false, we see here that the thread will set its own value to false so that it can go back in if necessary. It goes ahead and does its critical section. It then takes its thread number, I, increments it and takes it the modulus of the number of threads running, basically identifying what the next thread in the group is. And then it looks for a thread that is not itself and is waiting, and it keeps looping through here. If it finds itself, it sets the lock to false, basically saying, okay, I'm done. There's nobody waiting. Otherwise, it sets waiting to false for the next thread in the group, allowing this loop to break. So this is a way that you can actually use mutual test and set to provide mutual exclusion and still allow for bounded waiting. So let's go ahead and take a look in the next lecture on how to implement this. This ends lecture 6.4 on how we solve the critical section problem with hardware.